All right, hello everybody, and welcome to Lesson 1 in Chapter 5, where we're going to talk about the free surface effect of liquids inside tanks or in flooded spaces. I'm Lieutenant Timothy Mueller, and let's get this video started. Now, up until this chapter, we've talked about things like center of gravity, how the center of gravity moves. We've talked about vertical rises and horizontal shifts in the center of gravity, as well as sine and cosine corrections. But in all of these models that we've done, we've only really considered water, diesel fuel, whatever is inside the ship as solid weights. But we know, just in experience in life, that if you have, say, a cup full of water, and then you tilt it to one side without spilling the water always stays level. That water line is always perpendicular to the force of gravity. So like I said up here, we've only been considering liquids kind of as solid weights. They don't really shift at all. However, we know that if we have a ship with some, we'll say, water inside of a tank here, if we incline it, we go from a state with these dotted water lines to a new state with all the water lines directly perpendicular to gravity. So what does this mean for a ship and its stability? Now, when it comes to stability, pretty much every single time we think about stability, we have to think about center of gravity. When we have a ship rocking back and forth, if we go into that inertial frame where we keep the ship still and the waterline moving around the ship, we can kind of think of the water going from one side to the other and it's kind of swinging inside of an arc. This causes horizontal shifts. Now, at different angles, we have different horizontal shifts. So is there any way that we can kind of diagram this and go back onto things that we've learned already and kind of make, not necessarily metaphors, but kind of make them similar in different effects? Well, actually there is. Let's go to this diagram here. So we originally have a vessel at this inclination of 0. So this waterline and this dotted line inside the tank. Then it gets inclined over a small degree. So it goes from this waterline to this waterline here, and inside the tank, it has this solid waterline. So we learned from Chapter 0, Lesson 1 and Lesson 2 about center of gravity and center of buoyancy. Now you see here, when we go from waterline 1 to waterline 2, we no longer have any water here in this kind of triangle, but we do have water over in this triangle here. That kind of looks like what we learned in center of buoyancy with the swinging of the center of buoyancy of the ship itself with the submerged volume. This is going to be very, very similar. So we have the original center of gravity of that water inside the tank at this location here, we're going to call lowercase g naught. So at lowercase g naught, or small g naught, when we incline over a little bit, we lose a triangle over here, but we gain that triangle over here, just like I mentioned in Chapter 0, Lesson 2 with the center of buoyancy. So it's going to swing in an arc, just like we saw with the center of buoyancy. And if you remember, the center of that arc, or the center of that whole circle around, was the metacenter. In the same way, there's a point that's going to be at the center of that arc. And this is going to be called a virtual point. A virtual point is something that isn't physically real. However, we're going to use it to model and make things simpler for us when we do calculations. So this is going to be a lowercase g, v for virtual, and then FSE for free surface effect. And as the ship inclines over to the other way, so we'd have a waterline like this, and the internal waterline like that, that small g would just swing to the other side. But it would always stay within this arc, having the center at that center of gravity. So now thinking about this, what is the free surface effect? Well, the free surface effect is a reduction in stability, or a reduction in initial stability and overall stability of a vessel due to that sloshing back and forth of water, diesel fuel, whatever it might be, inside of tanks, inside of flooded compartments, wherever there might be water, there's always going to be this movement of water going back and forth. With that movement causes a horizontal shift. And you can see here, we're going to make that horizontal shift modeled into a vertical shift. And if you go to the right side of the screen, I draw it out again. So here, let's say we have a tank and it has some water in it. Then we incline over a little bit. So we've lost this water here, we've gained it over here. Here is the center of gravity originally for the original state of the tank, the center of gravity of the water inside of it. And then here we have that G swinging through an arc. If we draw the center line of that tank right through here, we see that the righting arm, so if this is the center or the line of buoyancy of that vessel itself, so if we're thinking the tank is inside the vessel, the center of buoyancy may be more off to the right horizontally than that starboard bulkhead. But if we look at the righting arm from little g1 all the way to little z, all the way over to that line of buoyancy, that distance is the exact same as if we just took that point and went all the way up so it meets the center line. So this GV, which is the same as right here, the little g or the little g v FSE, this GV has a righting arm of this GZV, GZ virtual. And that right here, the fact that these righting arms are the same is the very basis of what we're going to see later in this video. Now, before going into the equation for free surface effect, I'm going to tell you what we've gone through so far in this video. We've learned that G moves in an arc in a behavior much like the center of buoyancy when we're talking about the metacenter, which we learned over on this side. And we also learned that these horizontal shifts in the contents of the tank, depending on the angle of inclination, can all be made much simpler by just imagining a virtual rise in the center of gravity. So horizontal shifts in little g can be simplified into a virtual rise in little g to little g v FSE. Little g being the center of gravity of the water inside the tank, or the diesel fuel, whatever it might be. V standing for virtual, and FSE being free surface effect. And I'm going to derive the formula that you're about to see in the next video. There's a little bit of calculus that's needed, and there's a little bit of linearization and assumptions. So it's not necessary, especially in damage control assistant school. In DCA school, you really don't need to know how it's derived. You just need to understand the formula. But I know that some people really want to understand where things come from, which is why I'm going to show you the derivation. So now, we know that this small g rises to some virtual g, but that doesn't mean that the ship's overall center of gravity changes by that much. So now, I pose you the question, how much is the ship's G, how much is the ship's center of gravity affected? All right, so we've already taken a look at how that little g with the changing in inclination can be modeled as a virtual rise in that little g, the little g being the center of gravity of the contents of a tank. Now, we've seen it goes in an arc and it goes up to this virtual point in the middle of that swinging arc. Now, let's zoom out for a second and see exactly what happens to the ship overall. We know that little g goes to this virtual center of gravity, but now what happens to the big G, the overall center of gravity of the ship? Now, like I mentioned, I'm going to derive that in the next video. Right now is not the appropriate time to do it because there's some calculus in it and some other things, and it's not necessary for completion of DK school or actually applying this method in the fleet. So the equation for free surface effect, by definition, is I, the moment of inertia of the free surface, divided by the submerged volume of the vessel itself. This symbol here being a capital V with a line through it. But we don't need to, if we make certain assumptions, we don't need to do any calculations for the moment of inertia. By definition, the moment of inertia of a rectangle, if we assume that the tank is rectangular, is B cubed times L divided by 12. And the submerged volume is the specific volume of the contents of the tank times the final displacement of the ship itself. Now, we see over here, B is the breadth of the free surface. Breadth being another name for the width. So that B would be this distance here, or down here, it'd be this. L, the length of the free surface, is that longitudinal length from bow to stern. So on these diagrams, it would be going into or out of the page here. Then specific volume is a specific volume of the contents of the tank. We know that seawater is 35, freshwater is 36, and diesel fuel is 43 cubic feet per long ton. And then this capital delta F is the final displacement of the ship overall. Now, like I mentioned, this here is how far the ship's overall center of gravity shifts virtually due to free surface effect. Free surface effect is expressed in linear length, so linear units of feet, meters, centimeters, whatever it might be. It's always going to be a linear length. Now let's go into an example real quick and see how we can apply this. So in this prompt, our vessel is currently drawing 3,000 long tons. We fill a centerline ballast tank with seawater of length equals 20 feet, so 20 feet into the board. B equals 15, so this width here is 15. And then H, the overall height of that tank, is 16 feet. And we're filling it to 50%. What is the FSE rise? So what is the free surface effect rise in the center of gravity? So first off, we know that we have a vessel originally at 3,000, and we're adding some weight to it. So we have to find out how much weight we're adding. If we're assuming that it's salt water, then we know that the weight added is going to be that volume, so 20 times 15, which is the length times the width, times 8, because we know the overall height of the tank is 16, but we're filling it 50%. If we're assuming it's a perfect rectangle, then we're only filling it halfway high. So we've got 20 times 15 times 8 divided by 35, which is the specific volume of seawater. And we get 68.57 long tons. That means in the process of filling that tank, we're adding 68.57 long tons to our ship that's originally drawing 3,000 long tons, giving us a final displacement, this delta F, of 3,068.57 long tons. All right, so now we take that information and we go into the free surface effect formula, which is up here, B cubed times L divided by 12, specific volume times delta F. We know specific volume already is 35. We know B is 15. We know L is 20. We solved for the delta F, so we have all the information that we need to actually do this calculation. Let's start with the numerator here. We see this B cubed times L. We know, because of order of operations, we have to do our exponents first. So this B cubed means we take B and multiply it by itself 3 times. So we take 15 times 15 times 15. Then we take that value and we multiply it by our L, L being 20 feet. We're going to get a number up in the numerator. Next, let's do our denominator, the bottom here. 12 is just a number that comes from physics, and we'll see that in the next video. Specific volume is 35 cubic feet per long ton, since we're dealing with saltwater. And then this capital delta F is what we solved for here, 3,068.57. We multiply those 3 numbers together, and we get the number for the denominator. Then dividing numerator and denominator, we'll get, so here's everything not worked out all the way, but all the numbers plugged into this formula, we'll get 0.052 feet. Which means that the overall center of gravity of the vessel here has now moved up 0.052 feet. So if we had an original kg of, let's say, 10 feet, now our kg, the distance from the keel to G, would go from 10 to 10.052 feet. Now let's take a quick look back at this formula and see what changes can be made and how that affects the overall free surface effect. We already know that the final answer that we get is going to be in feet, and it's going to be the actual rise in the center of gravity of the ship overall. So here we have B cubed times L divided by 12 times specific volume times displacement. When we're doing these problems, usually we're going to be concerned about how much free surface effect is affecting us when we take on damage. So our specific volume is very, very frequently going to be 35 cubic feet per long ton because we're assuming that we're being flooded with seawater. So let's just assume that it's always going to be 35. B cubed. This means that we're taking B, the width of the tank, or sorry, the width of the free surface, multiplying it by itself 3 times. And we're also multiplying it by its length longitudinally. However, we're only multiplying by it once, which means that if we double the width of the free surface that we're talking about, then we're actually increasing our free surface effect by a factor of 8 because we're multiplying B by itself 3 times. So if we double B, we just have 2 times 2 times 2, which gives us 8. So we know that B, because it's cubed, is the most influential factor in free surface effect. If we increase B, free surface effect is going to go up. So a longer width of a tank or width of a compartment that's flooded out is going to have more of an influence on free surface effect. Therefore, a larger rise in that center of gravity, which furthermore reduces our GM, getting us closer and closer to instability. If we increase L, it's also going to increase the kg, decrease our GM, but not nearly as much as if we increase B. Now, we see the denominator. If our denominator increases, then the free surface effect decreases. It's just like when you take 1/2, which is 1 over 2, increase that denominator by 1 and go to 1/3. 1/3 is smaller than 1/2. Even though we increase the denominator, the overall expression goes down. So if we increase our displacement, our free surface effect is going to go down. So if we had a vessel that originally drew, let's say 1,000 feet, or I'm sorry, 1,000 long tons, we would have much more of a free surface effect rise in center of gravity due to all of this going on, but we have less displacement. So there's less resistance of the ship trying to move. Before ending this video, what are some ways that we can reduce the free surface effect in certain areas? We know that we have to fill tanks with diesel fuel, potable water, aviation fuel, whatever it might be. How can we reduce this free surface effect and kind of regain some of that stability from the virtual rise in G? Here's 4 examples, and this list is not extensive. There's several other ways that you can do it. However, these are very common in naval architecture or what you can do as a crew on ship. Pocketing. We talked about the width being a very serious factor in the free surface effect, being cubed. If you fill a tank to, say, 95%, which is called deep pocketing, or if you take contents out of it, so there's only a little bit left, which is called shallow pocketing, when the ship tilts over a little bit, that free surface will go from a full width of the tank that we see here, or even longer than the actual width, and it'll actually pocket to one point. So let's say we're pocketing this tank, and we have it filled all the way to right around here. We're going to be doing deep pocketing. Then if we tilt the ship over, the waterline might rest somewhere like that. Now that, for our free surface effect, would be the contributing width to the formula itself. Originally, for our initial stability, we would be right here, so that would be our contribution in initial stability. However, at small angles of inclination, that width is going to get smaller and smaller and smaller. Shallow pocketing is the same, but it's just in the opposite direction. So we had this tank full. Now let's empty contents out of it and see what happens. So if we take the waterline to be right here for shallow pocketing, and we tilt over the same time or the same angle, our new waterline here, or the waterline or the contents inside the tank would settle out right about here. And now in this is the same concept. We now have less of a width of that free surface through the entirety of its inclination, whereas here we had very long width In pocketing, we start to diminish those widths. The thing about pocketing, however, is that the effects of it are extremely complicated, and it's very, very difficult to actually calculate how much of an advantage you get from pocketing. So it's considered more like a factor of safety when it comes to free surface effect. We consider free surface effect here with a full width on B to be more of like the worst case scenario. And then pocketing just kind of helps us to some degree when it comes to the actual real world movement of the ship. Next up here is baffles. And baffles just kind of restrict that free motion of the free surface from side to side. By restricting it, it causes all that water to flow through smaller holes. So it's still able to go side to side. However, it needs a lot more energy to go from one side to the other. It slows it down. Therefore, there's not so much of a force on one side when it goes all the way to, say, port, and then all that force transmitted over to starboard. Next up is surface permeability. Now we know that large compartments like machinery spaces, main spaces, whatever, something like that, we have large items in there. We have engine blocks, we have compressors, pumps, whatever it might be. This free surface effect formula here assumes that the free surface is completely intact. There's nothing poking through the top of it. Surface permeability, on the other hand, says that if we have engine blocks, say that the flooding goes halfway up an engine, when the water tries to go from one side to the other, it's actually going to hit those engine blocks before it goes all the way to the other side. Therefore, we're actually going to help ourselves a little bit in ship stability when it comes to initial stability and overall stability, because that water now, just like we saw with baffles, has to go further, it has to go around those engine blocks to go all the way to one side. That gives the ship time to roll back to the other side. And then sluice valves. We see sluice valves as a very common damage control, a way of fighting damage. It's just a valve that connects to wing tanks so that you can open it up and the two tanks will be equal, or they'll be kind of in theory one big tank, so water or diesel fuel will flow from one to the other. Or you can close those sluice valves so the tanks will be completely independent. Therefore, it changes the breadth, and depending on the ship's operating condition, it might be a good thing or a bad thing. You can just check your DC book or in other publications given to you by your manufacturer. All right, so this concludes Lesson 1 in Chapter 5 of Free Surface Effect on a Ship. In the future videos, I'm going to derive free surface effect. We're going to do some more examples. Then we're going to talk about free communication effect. Then we're going to derive free communication effect, do some examples there. Then we're going to have a summary and review where I make a much more complicated problem talking about free surface effect and free communication effect. But that's going to be for later videos. Till then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.